All right, so welcome back. Let's start with this example here. It said list below the measure radiation emissions in watt per kilogram correspond to a sample of these cell phones. So there are 11 different cell phones that were sampled, and this is a small sample size. Normally, we would check the requirements to show whether we have a sample that drawn from a normal distribution. And that's the lesson that we skip. We skip that normal quantile plot. So I'm gonna go ahead and just say that the requirements meet. Okay, so meaning that this sample here is from a normal population. Okay, so go ahead and just assume this is not really our main focus for this chapter here. We're just trying to get familiar with the formal procedure of hypothesis testing. So as far as requirement goes, we can go ahead and ignore that for now. So let's start with the claim. Okay, so if you read the problem, it says that use 5% significant level to test the claim that cell phones have a mean radiation level that is less than 1.0 watt per kilogram. So this could be an old example here. Nowadays is the safe level of radiation level of cell phone emissions is around 1.6 watt per kilogram. So as you see, these cell phone here, some of us probably don't know what they are. You probably weren't born during the time that these cell phones out. Look at iPhone, Apple iPhone 3GS, and that's like 10-15 years ago. Anyway, so we want to test the claim that the mean radiation level of cell phones is less than 1.0 watt per kilogram. Okay, so let's see that. Okay, so if this is our data, okay, so usually we're going to use this data to get sample mean and sample standard deviation. So let's start with the claim. So the claim in here, it's really clear that it's telling us the claim is saying that the mean level is less than 1.0 watt per kilogram. Okay, in terms of the wording, what that means is, okay, the mean radiation level of cell phones is less than 1.0 watt per kilogram. Okay. All right. Okay. So that's the claim. Okay. So in order for us to go ahead and do a finding, we're gonna go ahead and assume something is true. Just a single value distribution, and that is using where the null hypothesis come in. So we're gonna make one of these hypotheses the claim, either the null hypothesis or alternative. So first we have to define, or we start with the null hypothesis. So the null hypothesis is always defined as equal to that claim value. Okay, and really this equal here, this equal statement here, really this is mu greater than 1.0 watt, greater than equal to, sorry, watt per kilogram. But if we go with greater than equal to, that has infinite distribution. So we're just gonna go with the one value, which is mu equal to 1.0. That is the opposite to this statement here. Okay, so that's what we're gonna go with. So if that's the case, then if we're gonna assume this is true, and we look at the evidence, and the evidence doesn't suggest that this is true, then we have to support the alternative, and then the alternative is going to be, in this case, the alternative is going to be the same thing as the claim. Okay, so one of these statements has to be the claim. Okay, so that's how we do in this class here. So one of these statements has to be the claim. It turns out this is same as the claim, and then also this is a left tail test. Okay, and we talked about that in the previous lesson. Okay, so significant level usually we're given in the problem 0.05. If not, use 0.05. So when we do the test statistics, it works as we say, okay, let's start with the assumption that we always assume. Let's start with this assumption that H naught is true. Okay, suppose the null hypothesis say that the mean radiation level for cell phones is around 1.0 watt per kilogram. Suppose that's true. Okay, then we draw a random sample from it. Then what we try and do is then we want to see how we want to answer this question. How significant, if that's true, how significant is it to find a random sample of cell phone with a sample means of 0.938 watt per kilogram. And where I got that number from, if we were to plug this into our L1 data set and then compute 1 var stats to get the mean and the standard deviation, we would end up with, the sample mean is 0.938 and the sample standard deviation is 0.423. And I'll let you guys work on that on your own. I'll let you plug this into the L1 column and then do the 1 var stats to get the sample mean and sample standard deviation. So let's go back to this here. So suppose the mean radiation level for cell phones is around 1.0 watt per kilogram. How likely is it? What's the chance? Is it significant to find 11 different cell phone with a sample means of 0.938? Well, I mean, if this is true here, guys, if this assumption is true, then this random sample means that we can obtain from this data here is going to be pretty close to 1.0, right? So to answer how significant is this, 0.938, that's only about 0.062 away from the claim value. So is that significant? Well, let's find out here using this formula here. So we don't want to be subjective here. We want to plug in the formula of test statistics and see what it comes out to be, so that way we'll be a little more objective than subjective. So let's do it. Okay, let's see the test statistic form. Let's call this T star. Okay, it's gonna be x bar minus mu over s square root. And remember, mu is the claim value. Okay, so x bar we found from the data, that's 0.938. Mu is the claim value of 1.0. S is the sample standard deviation. N is the sample size, which is in the case is 11. Okay, if we plug that into a formula, or calculator, and do the math right, it's going to be negative 0.476. Okay, what this number means, is that, this means that the sample mean that we drawn from the assumption that the null is true, the sample mean is less than 1 standard deviation below the claim value. The claim value is the mean there. Okay, so you tell me, if a data value that is, if a sample statistics is about not even close to one standard deviation below the mean, is that considered significant low, or is it not significant low? Right? From the previous chapter, we learned that anything within the 2 standard deviation of the mean, that's considered to be not significant data value. So in this case, we kind of know that an x bar of 0.938 below the mean of the value of 1 is less than 1 standard deviation. So that's not quite significant at all. Okay, well, the p-value would tell us, the probability of obtaining this would tell us. Okay, so that's where we head next, right? What is the p-value right here? So that's asking what is the chance or the probability of obtaining such sample statistics or sample x bar if h naught is true. Okay, so this part right here will answer that. Okay, I'm gonna show you 2 different approaches again. So the p-value approach is most preferred and the easiest one, and I'm also gonna show you guys how to use technology to do this as well. So using the p-value approach, we're gonna so p-value approach. Okay, we start out with do a TCDF. So we want to see what is the probability TCDF, because we're using t-distribution, what is the probability of obtaining such sample? So the 10 here is the degree of freedom there, guys. So that's the degree of freedom. Okay, so if we do that in our calculator, let's see what we get here. TCDF 99 if 0.476 comma and then 10. Okay, so we get around 0.322. Okay, around 32% chance of obtaining such sample data. And when we do the geometric interpretation, we draw the bell-shaped curve, this t distribution here. All right, and then we label the mean is, which is the claim value, right in the middle. And then we say the test statistics is here, negative 0.476. And we say, what is that probability? What is that chance? What is the chance of obtaining such sample mean? So this test statistics, this is where X bar is. Okay, so the chance of that is around 32%. Okay, that's the p-value. Okay, and then we're gonna make a note that p-value is greater than alpha, or significant level. Okay, so that's the p-value approach. To do the critical value approach, okay, we're gonna set up the boundary critical values to separate the non-critical region from the critical region. So let's start with alpha. Okay, alpha is 0.05. Degree of freedom is 10. It is a left tail test. Okay, that means to get the critical value of t 0.05 is going to be invert t. 0.05 degree freedom is 10, so that's going to give us a negative 1.12. And then we draw our bell-shaped curve to indicate that. Okay, all right, so here's 0, and then here is the t alpha, so that's negative 1.812, and then we're gonna say this here is the critical region. All right, so that's the critical region, and then that critical region has a value of alpha equal to 5%. And then over here is the non-critical region. Okay. Well, where does our test statistics fall under? Our test statistics is somewhere right there. That's our t star. Our t star is here. This negative 0.47. All right. So that right there is negative 0.476. That means the sample test statistics fall in the non-critical region. Okay, if it falls in the non-critical region, then we don't reject the null hypothesis. Okay, so remember that. Okay, so you either do one of these methods. So the p-value approaches, I think most students will go with that. The critical value approach is a little more confusing because it's some student calculator doesn't have the invert t function, right? Anyway, so now we get to the conclusion. To write the conclusion, right, the very first thing we want to do is we want to, explain our decision whether or not to reject the null hypothesis. That's the first thing we'll do, okay? So we always start with saying that at the 5% significant level, okay, meaning with the 5% chance making type 1 error, okay, our findings say that p-value is greater than alpha, okay? This implies that we do not have sufficient evidence to reject the null hypothesis in favor the alternative. Okay, so this saying that, hey, at the 5% significant level, we look at the sample data, assume that the null is true. We find that the sample statistics is reasonably close to the null. The probability of that is about 32%. We don't have enough evidence at all to reject the null hypothesis is false, and we can't really favor the, we can't favor the alternative. Okay. Now, when we get to this part here, we could have used the critical value. Instead of saying that the p-value is greater than alpha, we could have said at the 5% significant level, test statistic, we said test statistic falls in the non-critical region. Therefore, we don't reject the null hypothesis. We fail to reject the null hypothesis in favor of the alternative. All right. Moving on to the second sentence. The second sentence, what we're going to do is we're going to address the original claim. So we're going to say, since we fail to reject the null hypothesis based on our evidence and not favor the null hypothesis, the alternative. So we fail to reject the null in favor of, let's do in favor of the alternative, alternative. So this means we don't favor the alternative because we fail to reject the null hypothesis. Okay. So because of that, and since the the alternative is the claim in this problem. Okay. So the alternative is the same thing as the claim. Okay. Because we don't support the alternative and the alternative is indeed the claim. What does that say? Okay. We say that thus we do not have enough evidence to support the claim. And the claim was that the mean radiation level of Cellphone is less than 1.0 watt per kilogram, or data say that that's not quite true here, or data say that it suggests that the Cellphone radiation level is pretty close to 1.0 watt per kilogram. Okay. So I'm gonna let you guys just kind of play around this, take some notes, and save some questions on next week, and I'll do more example live on Zoom here. I don't think one example is enough, but I think one example is enough to get started with. I don't want to overwhelm with doing 10 example.